is not easy. Astronomy is hard, astrophysics is harder. And just as most people do not understand what they are looking at, if they even bother to look up at the stars, those of us who are not entrepreneurs tend not to perceive the complexity of a successful business. We speak easily of the thermonuclear reactions that change hydrogen into helium, but we know also about carbon stars. And so too do we seldom take a second glance at the corner convenience store on our way to the multinational big box store. Tom Field majored in computer science at Tufts University in Boston and then at Washington University in Seattle. He was one of the 8 employees who founded QuickPen in Englewood, Colorado. Hot young stars have a lot of energy. He started in software development, but soon found that his skills with people put him in a sales booth at technology trade fairs and software conventions. QuickPen specialized in software for structural and mechanical engineering with products supporting computer-aided design for heating, ventilating, and air conditioning. We compress 13.8 billion years into a colorful diagram and think we understand the universe. So I'm going to say that 30 years later, when QuickPen had 80 employees and Tom Field was vice president of product development, the company was sold to a multinational. Trimble of Sunnyvale was founded by former Hewlett-Packard employee Charlie Trimble. They now have offices in 40 countries. They market to agriculture, construction, transportation, and forestry. Tom Field planned his next phase, turning to his own hobbyist passions in astronomy. He founded Field Tested Systems in 1995. In 2011, he started writing for Sky and Telescope and became one of their freelance editors. 5 years later, he left Trimble and devoted himself to us. As I said, this stuff is not easy. Hanging out with astronomers, you meet a lot of bright stars. But every now and then, you come across a blue supergiant. Allow me to turn the meeting over to our guest, Tom Field of Field Tested Systems.
Thanks, Mike. Wow. I mean, I don't know where you found all that information online. I guess there's no way.
I've been stalking you.
I was going to, actually, that's why I paused, because the word stalking came to mind. I went, no, I'm not going to go there. Good evening, everybody. By the way, before I share my screen, I wanted to show you something that can make Zoom meetings a little easier. Some of you may be familiar with this already, and that is, you may just be seeing a big image in the middle of your screen of me with just a little strip across the top. There's a different way to view the screen. If you look in your upper right-hand corner, you'll see this view button that I'm showing here. If you click on that button and select Gallery View, then you'll get to see like 25 little video feeds at the same time. So if you don't have the gallery view up, I think you'll find that that makes it more fun to socialize, because that way you can watch people as they fall asleep or, you know, whatever they're doing.
We call it the Hollywood Square, the Hollywood Square view.
Yeah. So
that's why I don't have a camera.
Thank you for inviting me tonight. And Mike, thanks. You know, there's a lot that goes on behind the scenes, as those of you who are part of the board in these clubs know, to make these kinds of talks happen. And I appreciate the coordination and the work that goes. So we're going to make it easy tonight. What I'm going to talk about is really pretty straightforward. And during the Q&A afterwards, and I'll talk for like 45, 50 minutes. During the Q&A, I got an example, a little video I can show you of a spectrometer on the sun, where you can see the features on the sun. Those solar telescopes are pretty amazing, and this is just another step. I sort of feel, because we've been at it for an hour, that we ought to take a break. So I'm just going to rattle on here. Don't hesitate to get up. And in fact, I ought to get everybody up to do some jumping jacks or something, just to get your blood flowing. You've all had dinner, and I know it's, what, about 8:30 there. Thank you, Terry, on a Yang and Yin t-shirt. That's just what we need. Either that or those are some really huge sunspots and a weird form on that.
Yeah, I got this in Casper for the solar eclipse about 3 years ago.
Perfect. It's nice. Okay, so let's share my screen. And if we could, maybe I'm going to mute everybody. And let's see, you can unmute yourself, but I'd prefer, if you would, to hold off until until after my talk to ask questions. So let me share my screen and we'll get things started. So there's that. And what I really wanted to share was that. Terry, you can see that prism there. Shake your head yes if you can. Great, thanks so much. Wave your hands if anything goes awry. And I hope in terms of what's being broadcast on YouTube that they can see me, because I do have some show and tell. I love keeping astronomy weird. So whoever came up with that, my hat's off to you. That's great. So how have we managed to discover so much about the universe when, you know, we've really just barely stepped outside our own front door? And you know, we can see images of the universe in 2 dimensions. We can get a fleeting glimpse of a 3rd dimension of, you know, distance when we have an eclipse. And if we wait a while, you know, the time dimension, we can see things changing. And you can see there some stars going on and off, especially in the upper right-hand corner if you're having trouble finding them. If we spread the colors out, we get this as if 5th dimension. It's beautiful aesthetically. I love the colors. These aren't some designer's colors. These are, you know, nature's colors. And those gaps reveal an enormous amount about the stars. We're going to move quickly. I'm going to spend a little bit of time just talking about the science behind what we do to get everybody to the same level. We're not going to have to understand a lot of the technical details of the equipment, or even, frankly, a lot about the astrophysics that goes on, because, frankly, I'm being honest here, I don't understand a lot of it either. You know, we can do a lot of cool stuff in astronomy. I've got to stop spitting, you know? So we can do a lot of smart stuff in astronomy without understanding the details. And the beauty is that we can learn as much as we care to know. You know, there's no quizzes or final exams. And observing it just for the beauty of it is the start. And then as we choose to, we can get into more of the science. So these gaps in the spectrum reveal things about what we're looking at, whether it's our star or other stars. And I'm not going to read the bullets because I know at least that much about giving PowerPoint shows. By the way, I'm going to show you examples of some of these as we're talking tonight. I'm really glad that I'm talking about science that's well settled, because this week or this last couple of months, if my PowerPoint show related to current events, I'd be up all night every night revising it. So this is a pretty stable show, and it's one of the reasons I think that we like astronomy, because things change very slowly. A little bit of the science, as I mentioned. Sir Isaac Newton was the first one to split light through a prism, white light, becoming a rainbow. And then you can also split light if you just bounce it off of a finely lined surface like a DVD, or through a finely lined surface. Real quick, a little bit of the science. Some of you may be familiar with the science here, and that is Bunsen invented his Bunsen burner to burn a sample like this one over here. And the light goes through a prism, and then I should have learned how to draw an eye. That's an eye, but it's backwards. So, but if you look here at that light that's split by the prism, you get to study the properties of whatever you're burning in that Bunsen burner. By the way, one cool thing about Bunsen burners is Bunsen invented the burner, and he deliberately didn't patent it. He said, this should be available for humanity to further science. Now, of course, today an inventor of something like the Bunsen burner would have 10 patents. So this guy over here, Kirchhoff, we won't talk much about him. He was a contemporary and a colleague. Just one quick thing on this next screen, if we can get there, and that is, you're going to see examples tonight of spectra that have a rainbow, like in Roy G. Bivet order, right, from red to blue, with gaps. But you'll also see examples of emission spectra, where it's more or less black in the background, and you just have emission or bright lines. Now, which one you get, regardless of which one you get, notice the lines are in the same position. So, and which one you get, whether you get absorption or emission spectra when you split light through a prism or through a diffraction grating, depends on things Kirchhoff talked about. We won't talk about much tonight. Basically, the temperature of any gases, the light's moving through. And again, this is one of those places that you can drill down and study more in detail if you care to. So these are like chemical fingerprints, forensic fingerprints. And you can see that each element has a different fingerprint. This hydrogen line, for example, here just doesn't appear under helium. In fact, the hydrogen lines are so common in the universe and so frequently used that we've given them this name here, the hydrogen bomber lines. When I say we, I mean the collective scientists of humanity. I don't really consider myself part of that group. Humanity, yes, but scientists, no. So notice that we've actually named some of the elements here, much like we name the constellations in the stars in the constellations in brightness order by the Greek letters. This isn't by brightness, but they do have names. And we're going to see a lot of these hydrogen alpha beta lines. This beta line is sort of in the robin egg blue region of the colors. And again, we're going to see those as we go forward. Here, a little tiny bit of science. I'm going to go off camera to wipe my nose. Jeez, TMI, I think. So what I wanted to show you here, notice that hydrogen has a very different fingerprint than helium. I love this. This is actually a poster that I created some years ago. We sell them mostly to teachers, observatories, and some amateurs who are really hard-on fanatics for the field. This is a view of my software. Well, I'm not going to get into a lot of detail. We don't have to burn things anymore in the lab, thank goodness. We use these tubes you can see here on my video feed. It's like a fluorescent gas tube. It's got a gas in it. This one you can see there, maybe the lettering, helium. And can I get my camera to point to that? There we go. So if I turn that lamp on, you can see there's a helium spectrum. And in the lab, in physics classes, in fact, after I started creating products for amateurs, more for myself early on, and I'll talk about that in a minute, I realized that educators really could use a tool like this in the classroom. And I created this little camera here that, you can see the size of it there. It's pretty small for use on gas tubes. And that's been really popular with the high schools. And I wanted, again, I'll talk a little bit more about the kinds of things you can do in classrooms in a few minutes. Well, in fact, let's hold off on that. So far, everybody that I've talked about, old white men. Let's talk about some of the other contributors to the field who have not gotten the opportunities or perhaps recognition. First of all, Annie Jump Cannon and her team of women called computers. They were prohibited from accessing the telescopes at Harvard. And so they ended up, to our great fortune, but, and maybe there's two in the long run, hard to know. They ended up analyzing, no, it is easy to know. It wasn't their fortune. It was not their good fortune. They analyzed the glass plates from the spectrometers, the spectra of stars that were being captured. They were really good at it. And they ended up, as a result of their exposure to literally hundreds of thousands of spectra, a little more than a century ago, of coming up with a star classification scheme that, first of all, worked, unlike all the ones that had been created previously, but that really helped us understand the life cycle of stars. Here we've got Priyamvada Nataraja. She's at Yale, and I'm going to refer to my notes here if they haven't fallen off the little monitor. You can see here's my notes. She has studied, and the reason I have notes here is this is a relatively new slide for me. It was really astonishing for me when I started researching some of these people and realizing just how many are out there. Priyamvada has basically been studying dark matter and dark energy and gravitational lensing around black holes. Nancy Grace Roman, she got her PhD in the late 1940s as a woman, quite an accomplishment given the climate. She was the first astronomer at NASA, a big fan and promoter of the HST, the Hubble telescope that you can see behind her there, thank goodness. Elisa Quintana studies exoplanets and has discovered some that are in the Goldilocks region where they might have liquid water around a star and thus perhaps more likely to have life. And finally, Jedediah Eisler, she's at Dartmouth and studies hyperactive supermassive black holes. So we've come small ways. There's a lot more that we can accomplish in the coming years in enabling other people to get access to the kinds of opportunities that many of us have had. So I want to talk tonight about this little grating here. It's called a star analyzer grating. We sell it for about $195. It's got a whole bunch of, that's a technical term, a whole bunch of fine lines in it. It's called a diffraction grating, and it's in an 1.25 inch filter cell. So you can just screw it onto most equipment. For example, you could screw it onto a DSLR here. We actually also sell this inexpensive adapter to get the grating threads down to 1.25 inch here. But you can use a cooled FITS camera, uncooled. You can use, I've got one here to wave around in front of the camera. This is a ZWO. This is the 178 color camera. Doesn't have to be color. In fact, mono is, as you know, if you've done any visual imaging, is more sensitive and scientifically more accurate in some ways. But color also has the added benefit of showing a color spectrum that you'll see in just a minute that's more intuitive to newcomers. And down in the lower corner here, we can see even in a filter wheel, you can mount the grating. Lots of ways to mount these things. You can piggyback a DSLR. Tracking is always nice. There is a way to do it without tracking, but it's fairly challenging because with just a DSLR, still, if you don't have a go-to mount, you've got to find your target. You've got to get things oriented right and let things drift through your field of view, but it's doable. So, okay, all that's behind us now. History, theory, equipment, done with that. Let's get into the fun. What can we actually do? Well, we put the starlight through a grating and we get that spectrum that you can see down here on our sensor. There's the starlight. Some of it just goes right through the grating, doesn't get bent. But now the grating acts just like a prism. And it's above my pay grade to explain how that works. The Etalon that we saw in the Lunt and the other solar telescopes in the previous presentation, there's some really complex physics there and relatively new physics. This is pretty straightforward. It acts just like a prism. So here's our first wonderful example, done with an 8-inch Newtonian and an imaging source video camera by Torsten Hansen. Each of these is a spectrum captured of a different star. So they're not all captured at the same moment. The stars are in order of temperature here. So if I can find, there's my mouse pointer. These are the hot B stars, and then they get cooler stars as we go down this way, down to type M stars and K stars. So right out of the gate, you can see that star spectra differ by temperature. This is really the heart of enormous, like 50 to 80%, who knows how you'd measure it, I wouldn't, of measure what? Of the research that gets done in astrophysics. I mean, really, almost everything we know about the stars we've done using spectra. So even if you're not an imager, I should have said this in the beginning, because some of you are sitting there, you're armchair astronomers, maybe you're visual observers, no problem. Still, what I found is the more I understand about what I'm looking at, the more interesting and more rich my experience is visually or even just capturing visual images. So even if you never plan to do any of what I'm talking about tonight, I think you'll find an understanding. I know you'll find that an understanding of what I'm talking about, not that you need to be active and be able to give a lecture on it tomorrow or pass a quiz, but being familiar with it so that you're comfortable with, oh yeah, they're splitting light, looking at gaps. And look, I just want to show two quick examples on this screen. It is hard to find my mouse. There it is. So the first is, look at those wide dark areas there. Those aren't lines. Those are like forests, right? And they're just on these cool type M stars. We don't see those up here on these hotter stars. What's going on? Well, again, these are bands that are caused by molecules, not like hydrogen and helium, but complex molecules that are on the surface, the atmosphere of that star. And as the light goes through that more complex gas, there's very complicated interactions at the quantum level, they say, I think Richard Feynman said that only 3 people really understood quantum mechanics. It's like, phew, that's a relief for me. So cool stars have bands because of some of the molecules on them. These happen to be, they say, titanium. Oh, you know what's going on here? Is I forgot to tell PowerPoint, don't turn off my freaking cursor. Now, why they don't let me set this sticky permanently is beyond me. So, but anyway, this is titanium oxide. That's what's causing this absorption feature. And frankly, that's all I know about it. You want to read more about it? Great, you can, just like I could. What about this feature here? What do you see? What difference is here? Notice this one is darker on this type A star. So what's going on is, again, just real quickly, the Bohr model of the atom has these concentric shells that electrons are going around in, and they jump on occasion between shells. And when they jump, they can give off light or absorb light at certain characteristic fingerprint wavelengths. So on a type A star, the jump from 2 to 4 is creating that, what's color? This is sort of in the robin egg blue area. This is the hydrogen beta line. When an electron is jumping between 2 and 4 or 4 and 2, you get a feature right at this wavelength, 4800, this robin egg blue. The hotter stars, these type B stars, the electrons, when they're jumping, they're so energized by that extra heat that they go right past level 4 up higher. So you don't get a transition between this level. That's why the feature is less broad and less dark on these hotter stars in this type A star. The cooler stars, just the opposite. A lot of the electrons don't get pumped up to level 4 so that they remain at 2 or 1 or a lower levels, no lower level than 1. Let's rewind the tape. We'll edit that part out. By the way, my wife always emphasizes that I should dress for success, and I think this is probably the opportunity given the screen that we have here. I'm pretty sure, in fact, I'm certain this isn't what she meant. So, but you're talking hydrogen alpha right in through here. And, you know, the thing is, you know, this is one of those true confession moments. We're all about color here, right? In spectroscopy, if you look down at the bottom here, the root, it's not quite red anymore. There's a little bit of gray creeping in. Now, I know some of you have had this experience at home over the last 10 months. And that is, I can't get my salon to answer calls. They're not open. They can't make appointments. And so we're all facing that problem, whether you or perhaps a spouse. But anyway, my wife has told me this isn't what she meant, but dress for success is what the name of the game is. So suppose I said, do you see a little dimming right there? I mean, maybe you can. I don't know whether it's my imagination in that robin egg blue, but suppose I captured this spectrum. This is the first spectrum I captured, by the way, ever. And I tried to publish a paper and I said, yeah, right in the robin egg bluish area, there's a little dimming. That's not science. To do science, we need to be quantitative. So here's what we do. We graph it. How do we do that? Well, the star is very bright. This is an intensity axis here. So this peak is very high. And they're very narrow because the star is not very wide. But this over here, that thing's really wide. So this is really wide. And it's pretty dim here. And then it gets brighter, 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 and then dimmer, dimmer, dimmer. So this is dim, brighter, 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 dimmer, dimmer, dimmer. But look at this. See that dip? That's the heart of everything we're going to be talking about tonight. When we graph the intensity of this area, it becomes very clear. Now we're doing science. Now we have an instrument, we can measure how wide that feature is, where is it located, how's it compared to other stars, or this star tomorrow night or next year, other instruments, other telescopes, or your friend down the street. So how do we get that graph? So my story is I wanted to do spectroscopy. I don't exactly remember why, but I wanted to do some science. I got a grating. I put it on my C8 right outside the window here in my backyard, 3 miles from Pike Place Market. Set my C8 up one Saturday night, aimed it at Vega, and captured this spectrum. Came in at midnight. My blue jeans, my knees were grass stained because, you know, it's Vega in August. What do you expect, right? So the next morning I figured, okay, I just want to create this graph. And I tried some of the free software that was out there. And I gave up. I was so angry. I mean, learning new software is always a challenge. I'm not a patient guy. You, like me, you've learned software in the past. This software was crashing. One of them wouldn't install. It was like DLL hell, if you're familiar with that. They were both in French. There's nothing more, there are lots of more frustrating things than this. But one frustrating thing was an error message would pop up in French, and then when I'd click oui, the whole program would crash. So I told my wife I'd give up. I took the grating and I put it in a drawer. I said, life is too short. This is a hobby. And I'm supposed to be having fun. Well, yeah, sure, a little frustration here and there. I gave up. But over the coming weeks, you know, like I'd be sitting in the kitchen eating lunch or whatever. I really wanted to do this. I kept thinking about it. So I figured, okay, I'll just write a piece of software, you know, next weekend, I'll write a piece of software. Saturday, I wrote something to create this very graph. And one of the obstacles, oh yeah, I forgot. One of the things that I wanted to do, I don't know if I've got it here. It's sort of a cheap trick, but I used to have a slide with a lot of bullets in it about the key points I wanted to make. And then I realized nobody wants bullets. And so I gave that up. But I still want to announce key points with something. Key point is, one of the obstacles to getting involved with this is, oh no, I've got to learn a new piece of software. And what I want to do is, I'm not going to do a software demo. I'm not as dumb as I look. I know software demos don't work. It's almost 9 o'clock there. And, I can see the video feeds for some of you. And what I don't want to see at the tops of your heads is you fall asleep. So fortunately, you're muted. I wouldn't hear the snoring, nor would anybody else. This is my software. This is the very first spectrum I captured with my C8. Listen, I was not an imager. I mean, I'd taken a couple of videos of the moon, but so the reason I tell you that is this is one of those ding moments, is you don't have to be an imager to do this. Yeah, it helps. Yeah, you need to learn a little bit about exposure and focus and stuff. The cool thing is with the cameras today, these video cameras, you can do this real time with a laptop by your telescope. And then all the challenges that everybody who's been imaging for years and had to suffer through, you get to avoid, because now you've got real time. You can tweak your focus. You can change your exposure times in real time. And that's the R, by the way, in my software. RSpec stands for real-time spectroscopy. So let's spend just a minute looking at what happens. There's our spectrum. All you need to do is bracket in the star that you want to study. Can you see there's a gap there and maybe some gaps there, some dimming? And when you do that, here's the intensity graph. Look at all those dips. That peak there, of course, is because of this, the starlight. But then this is that. So big deal, right? There's a bunch of dips. So what? Now what? How do we identify what's what? That dip there, for example, is that gap right there. Well, the cool thing is, I didn't mention this, but when Bunsen was burning all those elements with his Bunsen burner, he kept a great catalog. And that catalog has now served us for, 150, 170 years. So the great grand catalog, meaning minor revisions, but not many, is now embedded into my software and is frequently available. I asked the software, show us where the Balmer lines, where those hydrogen absorption lines would be on this graph if the star has, any hydrogen in it. Who knows? Let's check. Wow. Look at that match. All those dips are going through lines that our reference says would be created if the star had some cool hydrogen gas in its shell. This is now, with a backyard telescope in an urban setting, how we can do science. We've more or less conclusively shown that we can detect the hydrogen of a star with a small telescope. It's a really remarkable achievement. The other thing I want to mention is this is not, oh, it is a ding moment. Oh, knocking things on the floor here. And that is, I did this in the city. One of the cool things, let me grab that. It was pretty indestructible. That was my grating I knocked off. One of the things that is frustrating us all these days is it's even more so now maybe to get out to our dark sky sites. I know the club has a couple of dark sky sites. I printed them out here and then I realized I'm not going to be able to pronounce Pedernales. Is that how you say it? And Inks I can handle, Inks Lake. You don't have to go out to those places to do spectroscopy. It's not like visual imaging where there's all this fancy tweaking and you need color balance and the more sensitivity you have, all that. Yeah, dark skies are better, but we're not interested in all those aesthetic adjustments. What we're looking for is these dips. Doesn't matter if they're deep or not deep. If we can see some dips, we're actually able to do science. So what I want to show you, just two more quick things and we'll leave the software. This is actually a freeze frame from a video I made with a webcam actually back then with the grating. You know, I took the barrel of an eyepiece and I, literally duct taped the eyepiece barrel to my webcam. It was a Logitech webcam and then put the grating right on it. So, but I want to show you that video because it's pretty cool. So that's now I'm playing that video. Our image is jumping around, right? Because of the seeing, the scintillation from the air currents. And so our data is jumping around. Now, this is really cool. I love showing you this. This will be the last thing I show you here. I'm going to zoom in on this feature. Let me turn off those lines. So we can see there's a dip there. Things are jumping around a fair amount. I'm going to turn on stacking. Stacking is when we add all the images together. Watch how quickly that dip and the spectrum stabilizes. All the noise, much of the noise has been eliminated by combining images. So you can do this real time under the stars. So final thing I want to mention is this is a great screen for outreach that I know I heard before the meeting started that you do an enormous amount of outreach. And by the way, your attendance numbers here are really great at this meeting. I appreciate people turning out and the club, having the draw to do that kind of thing. It's always fun to talk to a bigger group than 6 or 7 people. So when you show a screen like this, first of all, let's turn off that stacking or averaging. This is like a light to moths, people want to know, hey, what's that colorful thing over there? And this gives you a platform, a springboard to talk a little science. Now, there's not a lot of science that you need to get into. Again, you don't need to be teaching calculus or quantum mechanics. You'll learn what you need to talk about. Most people, it's surprising, and especially in areas that have more educational opportunities, economically advantaged areas, a lot of people are familiar with Neil deGrasse Tyson's Cosmos remake, and they'll go, oh yeah, that was in episode 3 or 4 that they talked about spectra. It always surprises me how much people know. Okay, I'm going to stop the playback here. The one thing I'd like you to do is in your mind's eye, if you could just remember, if I get the right hotkey, this screen here. Again, it's got this spectrum, right, with these dips, and I've got these little lines that tell us where to expect the hydrogen lines to be. It's like an overlay template, because we're going to see some cool science from that as we go forward. Okay, so let's pop up that. There's an outreach event, for example. They're starting with a gas tube. This is in France, but you can see how effective this kind of thing can be in entertaining a large crowd. Here's a wide field view with a DSLR. We're going to move pretty quickly here. We got a lot of ground to cover. Let me just tell PowerPoint yet again, leave my cursor visible. You can see these stars here. We've got stars with their spectra here. This star here has some blobs, technical term, right? Blobs. So these are emission lines, and they've saturated the sensor, so they're a little wider than the spectrum. In fact, let's look at a Wolf-Rayet star. Here's a confession. When Janet Simpson sent me this some years ago, I couldn't remember what a Wolf-Rayet star was. She told me that's what this was. Things do go in one ear and out the other. And what I found is when you get your hands on data, especially if it's yours, stuff begins to stick.
you begin to go out to your friend Wikipedia, you read about it, and because you have a conceptual framework already started, things hang around. So Wolf-Rayet stars, as it turns out, are late-stage stars. They've shed some of their outer shell. They have very intense stellar winds. They're probably on their way to being a supernova. Want to know more? Have at it. But that's what I know, frankly, about Wolf-Rayet stars. Let's look at the spectrum. I know a little more, and I'll tell you the rest of it right now. Look at these peaks around carbon. Why would we be seeing carbon on a star? Remember, a star fuses its way through different elements, and one of them along the way is carbon, and that's what we're actually seeing with the spectrum. And again, notice the really simple gear and short exposure time. So let's look at another emission object. There's our beloved ring nebula. You can see what hydrogen alpha and some, that Roman numeral 3 on oxygen just means it's ionized. Some of the electrons have been pulled out. So, but most extended objects aren't all that, aren't all that interesting with a star analyzer grading. We'll look at higher resolution device examples real briefly in a few minutes. But again, you can see here, these have slits. They're considerably like a factor of 10, an order of 10 more expensive and a lot harder to use because now we're on a 20 micron slit. I can't point my microscope or my telescope with that kind of precision or track. So these are cool devices, but nobody really starts with these high-end devices. I mean, by nobody, I mean almost literally nobody. So here's our beloved M42. Notice there's our hydrogen alpha emission line. And our ionized oxygen, there's that Roman numeral 2. Notice how, or 3, notice how narrow these features are. I'm going to actually stop sharing my screen for a second and ask somebody in a moment to unmute their mic if they care to. No requirement. I certainly won't call on anybody. And share with us the first time that you saw M42, the Orion Nebula. What was your experience? What was the telescope? Real briefly. Any takers? Anyone? Bueller? Anyone? Okay. Brian, you're muted. All right. So I think because nobody volunteered, Brian, it looks like you were still muted. What I'm going to do is I'll share my screen again, and you'll hear my brief experience. And that is in early 1990s, Shoemaker-Levy was coming, Shoemaker-Levy 9. I wanted to do astronomy. I'd seen great pictures over the years. I went to the Denver Astronomical Society. It's fun to remember when you didn't know something. I got out of the car and I looked out on the observing field, and what I saw, honest truth here, what I saw, those cannons that they shoot people out of at the circus? That's what I saw. I'm thinking, what are these circus cannons doing here? Of course, they were Dobbs, but I didn't know any better. I queued up. Somebody was running the Dobb, much like many of you or me. They were showing the Orion Nebula. I was all excited. They were talking about how cool looking it was. And I got up to the eyepiece, and my experience, and I bet many of you had this experience too. I went, so? It's a mono smudge. Who cares? It was only as years went by and I got the darker sights and I got a better telescope and actually learned how to use averted vision, and averted vision works really well at seeing extended objects like this. So I bet some of you still come back like me and look at M42. Why would we do that if it's just a smudge from the city, for example? Here's the deal. I mentioned earlier, real briefly, when you understand more about what you're observing, the visual experience gets that much richer. And that's what I found spectroscopy has done for me, is you start reading, you go, oh, well, maybe I'll read about why there's hydrogen alpha there. This is a stellar birthplace, right? A stellar nursery. We're seeing hydrogen alpha here, and I've never gone this direction in the show. But we're also seeing hydrogen alpha here on a late stage star like M57. Why, both ends of the life cycle, we're seeing hydrogen alpha. Why? So here's another example. These spectra here of Uranus and Neptune, notice these deep dips down here that are these wide bands. What did we hear about bands earlier? It means a complex molecule is absorbing some of the light.
What might that be on Uranus and Neptune? And by the way, this is also done by Torsten Hansen with a video camera. Well, how about the methane atmosphere on these planets? That's what we're seeing here with a backyard spectrometer like the Star Analyzer. It's pretty amazing we can do that. In 1881, Henry Draper observed the spectrum of a comet. The New York Times thought that was significant. Heck, if Hank can do it, so can we. Here's a spectrum in the lower left. You can see this beautiful string of gems. There's the spectra peaks called the swan bands, mostly carbon. This was captured by a guy named Vikrant Agnihotri. He's a nuclear power plant engineer in Rajasthan. He was a beginner in 2013 when he captured this spectrum. It's an extended object, so you might think, as I mentioned earlier, you'd need a slit. But as it turns out, it's a compact enough object that you can get interesting spectra just with the Star Analyzer. He was a beginner back then, and now today he's an expert, and I learned from him. And what teacher doesn't like learning from their student? I do a lot of teaching, a lot of support, helping people get started, looking at their images. It's what I love to do. I've got time to do it. So don't think you're going to be hung out to dry if this is something you try and do on your own. So here's a more contemporary example of the sodium lines in NEOWISE. So, anybody who uses a C-clamp as part of their setup, that's my kind of do-it-yourselfer. My problem is I break everything, and I would have tightened that C-clamp so tight I would have collapsed the housing. So fortunately, Robin Leadbeater didn't do that. He's the designer of the Star Analyzer, and he put it on the nose piece of a video camera, and he observed the Perseids, and he captured this spectrum. This is actually the meteor itself going through the field of view in one frame. It was moving pretty fast. And here's the spectra, and that gap right there is that dip, and you can see he was able to identify. Now, this is sort of a pretty esoteric. I mean, you got to wait for a meteor, for goodness sake. It's cold enough out there already. To wait all night, people do it. Why not? They have fun at it. So I'm not going to talk much about the flash spectrum. We saw a lot of it over the last couple of years, and will be a lot more talk about it coming up, except that yellow line, they observed on the sun before we knew what the heck it was. And so we said, well, we don't know what it is, but we know something about it. We know it's yellow, whatever's causing that fingerprint. In Greek, the name for the sun is Helios. We'll call this stuff helium. Now you fast forward 30, 40, 50 years, we discovered the same thing here on Earth. We were able to go eureka. That stuff that we discovered 93 million miles away without even going there, we now discovered here on the Earth. Pretty cool science. If you're into novae, some novae have deep dips like in this iron that doesn't occur in this one. Notice DSLRs are in action here. What's Doppler shift? Just a brief review. Most of you are familiar with it. If something's coming towards us, like a car or a train, its car horn is higher pitched than if it's moving away from us. So, the common example is a train going through a station, right, high, low. But even cars going past you with their horn, or even tomorrow when you're in the car on the freeway, I'm going to betray my ignorance and provincialism when I say I don't know. I'm sure Austin has freeways. Boy, open mouth, change feet on my part, huh? As cars go past you or trees go past you, you'll hear this high, low, right? You even hear Doppler shift on things going past you like that. Suppose we were expecting a spectrum to have this triplet, great word, almost self-defining. We expected these absorption lines, these three absorption lines right here, and instead we saw them down here over to the right. That would mean we'd call them red shifted because they were moved towards the red and the object was moving away from us. And the opposite, of course, with blue, the object was moving towards us. Let's look at a really cool example really briefly. An exploding star. So when two stars are going around each other, this slide or these images I pulled off the internet, I love it. A binary pair, wouldn't that be 4 stars? So when a binary system, when 2 stars are going around each other, we won't get into the details except somehow some of the gas on this one goes onto this white dwarf. And when that happens, you pour gas on something hot, it explodes, right? And there's lots of different types of stars that explode. This is what I just showed you, type 1A. There's other types where they run out of fuel and collapse, right? But let's look at this. In M101, there's the star. There's a photograph of another type 1A supernova, not the one we're looking at here, but you can see it's sort of, it looks like some sort of explosion, right? Some sort of sphere expanding. There's a spectrum captured by David Strange with just what is less than 15 minutes of integration time in a 9-inch telescope. There's the spectrum. And look at that deep dip there. We can barely see it in the spectrum mono, but there it is there. So, you know, we talk about standing on the backs of giants. The giants figured out that supernovae have their own fingerprints depending on what type they are. So one of a supernovae, that when these two stars share some gas, is a very different fingerprint when it explodes than one where it collapses because it ran out of fuel. Beautiful diagram here. When a type 1A supernova goes off, it's got a spectrum with a deep dip right in the blue here. And that blue, or purple in this case, where is this the first time I've used this slide? I was going, where's my blue? Where's my blue? This is off of with permission, a woman on the web who drew it herself, a postdoc. See that robin egg blue, as it turns out, that's ionized silicon. Not that it matters, except that it's nice to be able to talk about it. Look, these core collapse supernovae don't have a deep dip there. So this really is a fingerprint. And so David was able to say, this is a type 1A supernova. This is one of the things that professionals would like help on from us amateurs. And that is helping to identify supernovae. It's a little hard to do because almost all of them for the last 30 years or so are outside our galaxy, so they're pretty dim. But here's something really cool, and then we'll move on. If we measured what that exact color was, and it's at 6150 angstroms, that's the unit of measure we use for color. Now stick with me here, it's very simple. That's what David observed down here. Now let's go to Bunsen's records. Suppose he burnt silicon, beat sand. At rest, he would have seen the same dip at 6355. That difference is a Doppler shift, something's moving. Look, I didn't remember the Doppler shift formula. Wikipedia is my friend and yours. And when you plug the numbers in, you get to measure the speed with which that supernova shell is expanding towards us, the blue shift. There should be a couple wows there. First, wow, that's fast. Second is, wow, I can't believe I did that with just a small grating and a small telescope. So this guy, Adam Rees, you may remember, won the Nobel Prize in 2011 for observing the accelerating cosmological expansion. And what type of star do you think he might have used as a standard candle? A type 1A supernova. So now, once you've done this on your own or understood how it's done by other amateurs like yourself, now you have another way of understanding how that Nobel Prize was accomplished, what the data collection was about. Somehow I think his equipment was a little more sophisticated than our star analyzer. But in bang for buck, we do pretty well competing with him. So what about the spectrum of a black hole? Well, of course, a black hole doesn't emit light, but the accretion disk, as matter spirals in, that matter gets very hot and emits light. Let's look at 3C273. I've never looked at it myself. David Hayworth in Portland, Oregon did. There's the spectrum, two little dots of light. Let's zoom in. There they are. And there's the graph. Now this guy, I'm looking here at all the pictures here in the meeting to see if we have anybody young here. I'm not going to call on anybody and put them on the spot. It looks like most everybody's pretty old. When I do in-person meetings, especially, and there's some teenager, I may, without putting them in the hot seat, point out that this guy was just 25 years old when he made this observation in the mid-1960s. He was studying this and he wanted to figure out, well, what are those peaks? And he did science. He said, let me compare those peaks to some other things that we know about. For example, let's compare it to the hydrogen lines that we know Bunsen discovered and you saw in my software. This is the mind's eye screen I want you to remember. And boy, they don't line up, do they? So we're pretty sure these aren't hydrogen emission lines because they don't line up with hydrogen here in our lab sample or on Vega, except they do. And Martin Schmidt figured that out. And there's a great interview with him. It's a transcript. He describes his experience. It was too simple a solution. He was afraid he'd made a big mistake. He called his colleagues in. They all agreed it seemed like the right explanation for this. He went home and he told his wife that night, something terrible happened at work. Terrible. He's made this big discovery, this enormous red shift. What's terrible about that? He was worried about the publicity and that he wouldn't be able to do his work because he'd be so famous. So the significance of this discovery was that he was able to calculate the red shift, this distance, and we are too. You can see we got very close to it, and determined that this object was 2 billion light years away. Wow. The significance of the discovery was if this object is that enormous distance away, for us to see it has to be unbelievably bright inherently. And in fact, there's 2 great examples. I think one of the things we amateurs like is just how it's sort of the size stuff, you know. Man, it's big. The universe is huge. I think sometimes that it either makes us feel small and unimportant, or hopefully it just makes our woes feel unimportant. So, but 2 examples here. You've seen lots of examples of this kind of thing. For this to be as bright as it is so far away, it has to be 100 times brighter than all of the billions of stars in the Milky Way. And this example I like too. Now, Pollux, right? It's a star. We know stars are really a long way away. Not as far as other galaxies, but pretty freaking far, right? To use a technical term. And you can see there that if it was as far away as Pollux, it would still be as bright as our sun. That thing is bright. The thing that astonishes me is that this light has come from so far away and is so old, but it still has information in it that allows us to look at its fingerprint and tell something about that object. It's amazing. So not much in the universe ages that well. In fact, humans definitely don't. Here's Martin Schmidt a few years ago. And, you know, I've been justly accused of throwing him under the bus and, you know, basically throwing stones in a glass house. Look, he's got a full head of hair. I don't. I'm envious. Okay, get over it. Or maybe I should get over it. Okay, 2 more quick examples and we'll finish up. Thanks for your patience. So far, we've been looking at things that are, let's stick with this for a moment, hydrogen alpha, beta, gamma, like on Vega. And these are what? About 50 angstroms wide is about the smallest that we can see. Now, wouldn't it be great? Suppose we wanted to zoom in on that hydrogen alpha feature. I mean, wouldn't it be nice if we could just use our mouse roller wheel and just zoom in? But we can't, right? A lot of us tried that on the moon, right? I should have one to wave in front of you here, and I don't. But, you know, we've tried. Well, put more magnification on that. Let me see that crater up close, right? After a while, it's empty magnification. There's nothing more to squeeze out of that particular telescope and equipment and seeing conditions. Same thing with spectra. So in order to get the details, to zoom in, we have to use one of those more expensive slit spectrometers I mentioned. So there's Vega. This is that feature. And you can see there's a lot of detail in there. Let's do some science. Let's compare 2 known objects. Let's compare the Vega spectrum to the moon spectrum for hydrogen alpha. Look at the differences there. What's that? Well, the moon isn't moving towards or away from us. It's relatively in the same position distance-wise. So the Vega spectrum is shifted because Vega's radial velocity. This distance difference is too small to do unless you're using a high resolution spectrometer, right? 0.3 angstroms resolution. Can you imagine getting down to 0.3 on this scale? You just can't do it with a star analyzer. Last example, I promise. And there we're measuring the radial velocity. So here is a star, believe it or not. It's rotating. And this edge is coming towards you. This edge is moving away from you. So we've got blue shift and red shift. I can never remember which off the top of my head when I'm in front of a group. So Here's another way of looking at that schematically. Star's rotating. This edge is coming towards you, blue shifted. This edge moving away from you, red shifted. So what would happen to a spectrum of a star where it was really spinning fast? So we had a lot of Doppler shift from spin. God, that sounded wimpy. A lot of Doppler shift from spin. Notice that Altair is really, to use a technical term, smashed down, right? Some of the light that was here was spread over here. Some of the light that was here was spread over there. So we can, these giants upon whose shoulders we're standing were brilliant and are brilliant. Who would think that just by looking at the color of a star, you could tell how fast it was rotating? Or the color of a galaxy and determine how fast it was rotating? Or the differing colors of a galaxy determining how fast it's rotating and discover that it's rotating too fast to hold together by gravity. It should have torn itself apart. There must be dark matter. This is the kind of thing that when you understand spectroscopy, everything else opens up a little bit more. Okay, so real quickly, how do you get started? Star Analyzer, I've mentioned a couple times. Some sort of camera I've discussed, some sort of software. My software is $109. This is some of the freeware I mentioned earlier. It's good. They've improved and they're not bad, but it's a pretty steep learning curve. They're not designed by software developers. They're designed by really bright, capable people. They're friends of mine now. Also, you may need a little bit of a thread adapter, and that's because this distance here, while not critical, it's not like focus, it needs to be a certain distance, not too far away, not too close as a star analyzer. So, and there's a calculator on my site to help you figure that out, put your telescope's focal ratio in and stuff. And a lot of people just send me their equipment specs. There's a form to do that on the site. And I tell them, oh yeah, you ought to buy for like $10 a little spacer, an empty filter cell to move it a little further away, that kind of thing. So there's the calculator, and there's where I forgot I had this in here. Hey, it's been a month since I gave this talk. It's already fading. So there's the input specs you put in. If you get 3 green flags over here, you're good to go. So there's tons of neat books out there. This one in particular is cool because, and it's linked to on my site under links. There it is. Because the cool thing about this book is he shows you these really cool diagrams of what you can expect. And you can see he calls out, but listen, I'm a knuckle dragging programmer. I don't know the significance of ionized nitrogen or helium, but he does. And I don't have a slide of it, but the cool thing that he does is he writes prose to explain to us what we're seeing spectral-wise. And this is written for us, not postdocs, not physics students as undergraduates. So this is a cool book to understand what we're seeing. So we have a great forum where there's lots of help available. You can see some people doing solar spectra here. The AVSO is jumping further and further into spectroscopy. Again, Stella Kafka, their current executive director, great director, as well as Arnie, her predecessor. They're professional astronomers. They know the importance of this. They now have a spectra database that you can contribute to. I've given talks, gave a big talk to them, I guess this fall in a workshop. But 4 years ago, I gave a hands-on workshop at the SAS conference in LA, and everybody had their laptops and sample data. And here's great news. You can download my software for free for 30 days. The same page will let you download the sample data I used in that workshop, and there's a link to the YouTube video of my workshop. So tomorrow morning, it's Saturday after all, once you've got your honeydew list done, you could sit down, hopefully with 2 monitors, and you could go through that workshop. It's an hour-long workshop. When you're done, even if you never do any of this again, you'd be deep in. You'd have it in your muscles, so your muscle memory. Maybe not memory, but you'd I don't even have it in my memory. So there are opportunities to do pro-am collaboration. Everybody in this list, except for Bob Stencil, who's at the University of Colorado, are amateurs. So we've come a long way in the last 200 or 300 years, as well as the last hour or so. I ran a little longer than I hoped to. I apologize. We do stand on the shoulders of giants, and we get to give back and pay it forward. I know that you do a lot of outreach. I appreciate all that.
I hope you'll continue doing that when things open up again. It's nourishing, as you all know. It's a wonderful opportunity. I'd like to thank you all tonight for your patience, for at least some of you smiling at some of my jokes, not grimacing too badly. And I love answering questions. I will talk until we run out of time or interest. And you can see here contact information. There's a contact form on the site too. Easy to find on Google if you don't want to write this stuff down. So I'm going to stop sharing my screen for the time being, and we can open it up to questions and have a go at it. Thanks again.
Tom, I'd like to start with a question. This is Tim Brown.
Hi, Tim.
And am I correct? You did this for us many years ago over a webinar.
I might have, yeah.
You did. I was the vice president then and got you. I'm moving out close to you, by the way, soon. So
I heard that mentioned. Well, make sure to look me up. I'm here in Seattle, and
yeah, we'll be in Bellingham.
That's great. I got a cousin there. I'll be coming up. So this summer, as things open up, let's make a point of it.
Sounds good. We got a big house coming up.
Oh, good. Great. But get all the observing you want to get in before you come to Washington.
I know. It's the hard part. Yeah. Grandchildren make up for it. Now I'll shut up and open it to the rest.
Don't forget to unmute yourself if you've got a question.
Got a question.
Well, Tom, hello.
Hey,
is this working?
Yeah, Brian. Sorry that it wasn't working earlier. I didn't give you enough time.
Tom, go ahead. I think I figured this. I got this headset today. Go ahead, Tom. I'm just checking to make sure it's working.
Great. Somebody else.
Which Tom are we talking to?
Hey, Tom. There's another.
Hello, Tom. I've got a. So I was noticing in your software, you actually had the classification system for stars. So can you actually overlay like typo star over your spectra and try to determine whether or not it is that type of star?
Yes, you can. Thank you for asking that, Tom. I like your name and the way you think. So let me just really briefly show you that to give you an idea. So here, am I sharing my screen?
Yes.
Okay. You can see the software there. Good. Let's turn that off and just turn off the eye candy there. So there's Vega that I observed. Now, built into the software is a reference library of different star types. Again, this is most of what I'm talking about here I learned after I got into spectroscopy. You know, I sort of knew it, but didn't really understand the big picture. And that is that hotter stars have different Planck curves, Planck-like curves in stars cases. So for in this case, Vega, which is what we're looking at here for my first night out, is a type A star. So there in green, we can see Vega. So the first thing to notice is that there's a correspondence between this absorption feature, which is the hydrogen alpha, and that one, as well as these two, as well as these two. And there's really a correspondence between the professional data, although their dips are much deeper, much better full width half maximum. But notice that the professional data keeps going up as we get into the blue, and my data crashes down to 0. And that's because my camera and all of our cameras lose sensitivity as we get into the wings, into the red and the blue. So there's one step which I won't show right now that allows you to correct for your camera's lack of linearity in color. And so, yes, you can compare the shapes. And it's one of the things I didn't mention was on my site also are an enormous number of videos that you can watch where I walk through. There's no big complicated manual. You know, within 3 or 4 minutes of watching the first 2 tutorial videos, you're good to go to do the kinds of things I'm showing you tonight. But I wanted to show you a cool video that really was what I wanted to do when I first got involved in spectroscopy. So let me move this over here. So this is the spectra of Albireo A and B in mono, because it's more sensitive. And I'm now correcting for the fact that my camera is not sensitive in the same way to all colors. So there is my Planck-like temperature curve of the star. It's pretty noisy, and it's a hot star. So most of the heat is in the blue range, like in a candle, where the real heat in a candle is in the blue. Now let's play this video. This is actually live under the stars. It's jumping around because our seeing was changing. Now I'm going to move these orange lines and sample the other star. Watch how the shape of this curve changes. Alberio A is much, much cooler.
Mm-hmm.
So now we can see the shape change. Much like now, it's not quite a Planck curve because stars aren't black bodies, but this is cool and fun, but isn't the way professionals do it. Professionals actually look for features and know that different types of stars, and this is what Annie Jump Cannon and her women team of computers did, was begin to classify stars by, do they have a lot of hydrogen lines? Do they have a lot of, whatever, different lines, helium and so forth? It's a great question, Tom. I'm sorry to have taken the ball and really run further downfield than maybe anybody wanted to hear, but I appreciate your asking.
That was cool.
Good. I'm glad to hear it. I think it's cool too. And that's really, that very demo is what got me into all this. I wanted to know the difference in temperature between Alberio A and B. Other questions? Anybody else?
We have a couple of questions from on the chat, Tom.
Thank you, Dawn. Go ahead.
First is from Setwant. He says, if the spectrum is captured on the same sensor with the same imaging circle as the telescope, will it not be corrupted by the other stars, etc.?
That's a great question, Sawan. And it would be, except that we get to bracket in. You can see here on the screen. In this case, all I've got is Vega. But there could be stars all over the place, and none of them would affect this intensity graph. Let's close that green one. What an ugly color. That really is puke green. The only stars that would affect this intensity curve here would be stars in this region. And they can interfere a little bit unless you have a slit. Turns out it doesn't often happen, and there's ways around that also. You can just eliminate those points over here, or you can just rotate your grating a tiny bit so the spectrum is at an angle and isn't falling over top a star. So it's a good question, Salwan. Thanks for asking it. Clearly you're thinking about this. Other questions?
We have another one from Neil, who's asking, instead of focusing on a specific star, how would you analyze a large nebula region?
Great question. It's tough to do without a slit because what we're seeing over here, just to get technical for a second, or what we're seeing here is the star just repeated all the way, an infinite number of times all the way across. So if this is a blob, you're going to see blobs here and it'll be really muddled. You can, though, have some fun with that. I don't think I have an example here to show you, where suppose we had a big nebula here, we could sample different regions of that nebula, and we would be able to see differences. In fact, on my PowerPoint show, let's see if I can find it real quickly here while we're looking at it, is you'll need some Dramamine if you're trying to follow along. Oh, there it is. Look at, look at the difference here. I was all excited when I first saw this. So here's an extended object that you were asking about, Neil. And it's not a point source, right? It's extended. It could be a galaxy. And you can, some galaxies, in fact, we'll come back to that in a second. Notice that the red from the hydrogen alpha has a bigger hole in the middle or than the oxygen, or stated another way, this lifesaver-like shape is thicker here in oxygen than red in the hydrogen. I thought, oh, right, that's really science, There's more red on the peripheral than there is closer to the center. Well, this is just because my camera's response isn't that great. So this is not scientifically different data because the source object is different. But what I wanted to show you was, something called an AGN. In fact, I don't think I'm going to show you that right now, just because I don't want to drag us all over the place. If we have more time in a few minutes, I'll show you. You can look at galaxies if they're really compact and see their hydrogen emission. AGN are active galactic nucleuses, and you can actually measure the Doppler shift that's occurring. By the way, quick story, and that is when I published my first article in 2011 in Sky and Telescope, Bob Noye was the editor-in-chief, great guy. And I talked about 3C273 and that red Doppler shift. And Bob was a smart guy, great guy. And he's thinking to himself, Tom's wrong here. He's using the wrong terminology. And he sent an email to Adam Rees, who later that year won the Nobel Prize. And he said, Adam, Tom here in this article is talking about Doppler shift of this quasar because of cosmological expansion. Is that the right terminology? And he knew the answer. And Adam responded, no. And this is sort of cool just because it reveals the precision of language and the subtlety that professionals use. With 3C273, this is the first time I've actually gestured this way, way far away. First time in this talk. I've never done it in any talks before. And you think about it, it's moving away, I thought, so it's Doppler shift, right, from cosmological expansion. Anna Marie said, no, it's not called Doppler shift because nothing's moving. What? Nothing's moving? What do you mean it's moving away? It's redshifted. Yeah, it's redshifted from cosmological expansion. Space is expanding, but nothing is moving. Anyway, that's the closest I ever got to a conversation with a Nobel Prize winner. Other questions? Any other questions?
I have one. It might be a little bit too technical, but I'm just still trying to understand why an element like helium that gives off that alpha line, because an electron is falling back into its original lowest energy state shell, so it gives off that particular color photon.
Well said.
And then helium has the same thing. There's the electron falling back to its lowest energy state, and it's still the closest. Why would those two be different colors?
That's a wonderful question, Jamie. And there's a Zoom room full of people here, some of whom are going, I know the answer to that, and others who don't. And it's a great question. So the issue here is, and here's the cop-out, quantum mechanics. It's above our pay grade. But the real answer, or a simpler answer, and this is all I know about it, is a helium atom, those shells, those orbitals are in different distances because, again, the nucleus has a different composition, right? There's 2 protons and potentially neutrons. And so because the shells are different distances, the transition energies, which you so well described, are different. It's a perfect question. And it gets really complex really fast when you have something that has lots of electrons, meaning something further down the periodic table, like carbon or whatever. The transitions get so complex that it's again, hard for us mere mortals to identify what's what. But that's why they differ. Does that make sense the way I explained it?
Yeah, so basically the photon has, for like a bigger atom, the photon has to be higher energy, so it's a different color. It's more towards blue end. Okay.
Great, and thanks, Tom. See, I saw your acknowledgement that I was going down the right path. I appreciate it. I'm really faking it here, folks. I'm not an astrophysicist. I'm like I said earlier, a knuckle dragging tool guy. So just a programmer. So, and again, I tried to emphasize, I gave up on the ding. It's too tacky. But the thing is, and I said it a couple times, you don't have to know a lot in order to have a lot of fun. And you can ask questions of the sort you just asked, Jamie, or that Tom asked about, how do we tell star temperatures? Those kinds of questions are questions that you can get answered by other people on our forum or other places. I wanted to show, since we were talking star temperature, I don't know if this is going to show up. No, it doesn't really. These are different stars of different temperatures, and there's different features. For example, here, you can see in this column, you can't really see it, can you? Some of these features are deeper as you get into different stars. This is a hydrogen beta line. This is how professional tells star temperatures. Is how deep is that hydrogen beta feature? If it's really deep, it's probably a type A star. If it's really shallow, then it's either a really hot star or a really cool star. And those are fingerprints that are determined by the chemical composition. Other question? Oh, before I do another question, I wanted to show you another video. Am I sharing my screen right now? No, I'm going to share it. Okay, so this is going to be the hydrogen alpha sun. So this isn't something that I sell. It's always awkward for me in these talks because I think people think, oh, he's trying to sell us something. Yeah, I'm trying to sell you spectroscopy. I wouldn't mind making a few bucks, but I'm really just trying to sell you on the excitement of things. So this is a spectrometer. It's a solar spectrometer from Shellyak. Am I sharing my screen?
Yes.
Okay, thank you.
And there's an eyepiece here, and you don't even need tracking. Unlike what you saw from Mike earlier, you don't need the tracking like on a hydrogen alpha. And this has a prism in it. It's, or it has a grating of some sort. It's got a slit. But because it's such high resolution, the rainbow is so stretched out. For those of you who are grandparents, I don't know when you do this, where you say to your grandkid, how much do I love you? This much. Well, that's what the spectrum is spread out. So with a slit device like this, you see just a tiny little piece of the spectrum, some red here or some yellow here or green or whatever. So it has this little tuning arm here that lets you change where you're looking at. So let's play this video just for a moment. This is great for outreach, by the way. There's the tuner, where you get to specify where in the color spectrum you want to be looking with your little magnifying glass. And you can see we're pointed here in what's called the magnesium triplet. Turns out magnesium, again, for quantum mechanics stuff that's way, way over our heads, there are 3 lines where normally there'll only be 1. And there's a sodium doublet, same issue. But let's take a look at what through the eyepiece it looks like. Now, this is an example of how to make a really crummy video for the eyepiece. This I made for a friend years ago on our front lawn. So the real device is a lot more fun to look at. But there is, you can see that triplet there in the green. That's the absorption features from magnesium on the sun. Now, what I'm going to do in this next really brief part of the video is I'm going to move that lever to a different part of the spectrum. Look how the colors change as we're looking at different regions. And there's the hydrogen alpha of the spectrum. So this is a cool device. There it is again, a little gnomon to help you point it at the sun. There's my my Crocs on our front lawn. And there was one of the, I'm just final step here showing you the sodium doublet, it's called right there. It's really, the cool thing is just aesthetically, it's gorgeous. It's easier to see any of this than it is with to see, something through a telescope, because your eye doesn't have to be in the exact right position because it's this huge object you're looking at. Colors are gorgeous. This is a great tool to augment the solar outreach that you'll be doing. I love solar astronomy for outreach because I get a good night's sleep and because I get to see the faces I'm talking to, and there's young kids and it's the sun after all. And so in addition to the hydrogen alpha telescopes that you saw earlier, the Meads and the Lunts, this would make a nice tool for you for outreach. The only gotcha is it's not cheap. It's about $1,300.
Wow.
Is that why I don't have one of these yet?
Yeah, exactly. I saved that for the end because if I'd said that at the beginning, you all would have tuned me out. Anyway, cool device I thought you might be interested in knowing about for the future.
So you could stick a one-shot color camera, an astro camera in place of the eyepiece there, and it would give you high fidelity on the color.
Yeah, Terry. Yeah, you could use a phone if you wanted. You could also, if you cared to, you could just put an astronomical video camera on it, and then you've got the challenge of how to avoid the bright sun on your computer screen. But yeah, it's just a standard eyepiece, easy to focus, so easy to set up. It's a cool device.
These aren't common here, are they? We don't see a lot of these here.
Pardon me?
We don't see a lot of these Shellyacs here. I think I ran into one about 3 years ago at a daytime night sky festival that we did over in Dripping Springs, and a fella had one of those the first time I saw one, but I haven't seen one in person since.
I was going to try and find mine, but it's in the closet somewhere. I think the reason you don't see them, Brian, is they're expensive.
Have you priced a lunt recently?
No, are they more than that now?
I have more in that lunt than that Shellyak you just quoted. Yes, sir.
Yeah. Well, eventually somebody, one of the reasons I keep beating the drum on spectroscopy is the more of us there are, the more likely manufacturers are going to start jumping in and competing with simpler and less expensive devices. So that's another reason to get in. L high res light. I'm just curious what the cost is right now. Yeah, $1,400 from OPT. So
Quite
yeah,
reasonable, and you're probably not going to find a used one anywhere. That's probably a new quote price, whereas some of what we've put together that I showed earlier tonight and some of what I've seen other people put together traded on cloudy nights and what have you, and you can get into a single stack way under that. It's the double stack that pretty much doubles the price of the entire thing.
yeah. But I meant to mention, I wrote down a note when you were talking about that. I was multitasking while you were talking at certain points, but I wanted to mention, if you didn't bring it up, that the difference between the single and the double stack, in my experience, is that the double stack, the image, and you've probably seen this, Brian, is dimmer. So I find that it can be a little harder for people to see what I'm pointing out. But also the single stack is going to show prominences more clearly. The double stack is more going to show the surface granulation and the sunspots. The great thing is everybody has their own activity that they prefer. For me, I like showing the prominences because I think they're more dramatic. And I like to say, see that arch? That's like a McDonald's arch, except you could drive the Earth right through that arch. And that sort of blows people away. Everybody has their own sort of dance, though. For that
well, the other side of that, Tom, is all you got to do is reach up there and spend 15 seconds screwing that double stack off and set it on the table, and you go right back to single stack.
I didn't know it was
because it stacks. In most cases, it's just sitting in there like an eyepiece.
Oh, cool! So you get the best of both worlds. Yeah.
If you're willing to invest in the double stack, it was very eye-opening for me for surface details. You're right. That's what it is really good for, is contrast to surface details. Spectroscopy, of course, you're getting into the full range, and that's what I want to understand better as well.
Say, Steve,
go ahead.
Tom, do you know Stephen Ramsden?
Oh, yeah. Wonderful, great guy, a real friend.
Yeah, Mike, that's somebody we need to snag sometime, is to get a presentation from Steve Ramsden. But I would expect he's a consumer of some of your products.
He is. I think I gave him the products only. Consumer user, yes. Just because he's this guy who just gives. And ran into a problem right before the solar eclipse because the state of Alabama was worried about eye damage with the filters that he was giving out, and he pretty much had to back way off on the outreach he was doing. He has a van, he's got solar scopes in it, he was going to schools, and he's an interesting guy because he's and I don't think he'd object to my description. He's pretty rough in that he comes from a pretty tough background. He's a smoker, he's a big guy, but students really love him because he's authentic. He's different than the kind of polish that normally come before them. So yeah, he's a cool guy, and he has every solar scope that Lunt has ever made. He was helping promote their products. But I'll tell you an interesting story. When I went to Meade in like 2001, they had this thing called HOTS. It was a solar observing. It was a conference for a day or two. They're promoting their products, but we had a lot of interesting talks. At that point, Scott Roberts was VP of engineering. He's since moved from there to Explore Scientific, his own company now. And even there, it was clear he was on fire. A wonderful guy. He took us into the room where they make that Eidolon that you were talking about, this device that bounces the light inside. It's got some quartz in it. And he said, to be honest, this is like a black art. Some people have the touch to put these things together, and like even computer chips, some of them just never work. But some people have a much higher productivity and success there. Oh, there it is. Thanks for showing us that, Brian. You're muted again, Brian. Sorry.
Okay, am I on now?
Yes.
Hang on, there we go. Okay, this is the double stack on the front. You saw it took me 10 seconds to unscrew this off the front.
Yeah.
So I ran this single stack for 2 years before I found a deal of one of these used. But as you can see, this is this highly reflective glass, and this is what's called a tilt tune. It just does a very slight tilting between this little divider you see between here. You can see this in a shadow that moves when you're looking through this. It'll just take a little ghost image while you're looking at it there in the center. It'll kind of move off to one side or the other, and you can fine tune it. So it's really just two pieces of glass with a very slight tilt angle to them. Right. And the entrance on the front is very much the same thing. This one's 50 millimeter. That's what it looks like on the front. That's the back. So this is just another etalon. And like you said, it dims it down. So it gives contrast to a different portion of the sun.
Sure.
And that's really the whole thing. As far as how they're made, I know they're ultra flat and ultra precise. I've been reading about it on the Lunch site.
Yeah, they really are. Well, what other questions? Anybody have any other questions?
I have a question, Tom.
Great, Dawn, go for it.
So for those of us, much like Brian, that are spending their well-earned money on double stacks, what are some other tools or some other activities that you find are really great for drawing in, younger solar spectra astronomers, especially from an outreach standpoint, because we do cater to a lot of young astronomers. And spectral astronomy can seem probably a little beyond their reach at times.
Yeah,
I mean, obviously being able to show them something visual is always key.
Yeah. What I'm doing, everybody does outreach, has their own little spiel. The pause there was, I was debating whether to use the expression attention whore because I love attention. Basically, everybody has their own song and dance. One thing I like to do is, and I don't know how you do this with the group, with my Lunt, is I really, if somebody's interested, first of all, I have them sit on an adjustable chair. And secondly, I hand them a little clipboard and say, can you draw those after they've seen the sunspots, have them draw the sunspots. And I have them draw the sunspots. I have a clipboard with some small pieces of paper. I learned the hard way. You don't just say to an elementary school kid, draw the sun, because then they spend the next 60 seconds trying to draw a perfect circle. So now I just take a pen and go, see, oh, there's the sun. I just draw the sloppy thing so they get the idea. And then I coach them, can you see some dots, and have them put it, and that really, as you know, when you draw, you begin to see a little more. Now, the cool thing about doing that is the flip side has a handout on it. And this is a NASA image. And so I get to talk about the size of the sun compared to the planets. And this is something they can take home. And I'd like to think some of these end up on refrigerators under magnets at people's homes. The other kinds of things that I do when I'm talking sun, it's just standard stuff. And this you can't do at night, but I love doing it during the day, is I take a little, it's actually a little jewelry bead, like a BB, on a piece of fishing string so I can hold on to it. But I don't show them that. I literally have a basketball there. And I say, so if this is the size of the sun, how big do you think the Earth is? Then I show them the BB and I watch the parents' eyes behind them going, because people don't understand. And then I talk about the Earth going, what does the Earth do with respect to the sun? And most don't have an idea. So then, while I've asked that question, what I like to do is run in circles around the student, in a big circle, and pantomiming exhaustion. I need an answer. I'm getting tired. But what I do is, after that, I talk about how here's the Earth. This is when you were born. And then I go around and I show them when the Earth gets back to the same place. Happy birthday. You've gone around the sun once. They love that because it's now their birthday. And then to talk about distance, I just take that BB and I start running. Mm-hmm. And I just disappear on them. I go 25, 50 yards away. You can do all of that stuff with them. I don't know if that's the kind of thing you were asking about. I'm sorry for boring everybody with my own.
No, not at all. It's very much along those lines. I think a lot of it was just kind of curious on how to encourage or at least ignite the interest in spectroscopy.
In spectroscopy itself, it's hard to do. Yeah. I think with the sun, it's really hard to do. The best you can do is with colors. I've struggled. I've got I bought a prism here out of plastic that I thought would, be helpful to show the rainbow, and you can do that kind of thing. Interesting thing, by the way, I had to pull it from my show. I just didn't have enough time to include it. But for a while, I was, I had a photo. As it turns out, our eye gets worse as we age, as many of us know, and we lose the purple blue. And so if you were to just take a prism and show the spectrum on a white refrigerator or a white wall, the frustrating thing is, for those of you who are older like me, if you ask your grandchild or your niece or nephew how far into the blue purple they can see, point to it, they'll be pointing to a place you're not seeing any light at all. I mean, because your vision is just lost in the blue. So, and the cool thing is, am I sharing my screen now? Good, I'm not. Is there was an artist called Monet that some of you may be familiar with, who did this painting, which came up on my screen along with other things. God, it's on Etsy. No wonder there are things that I'm glad I wasn't sharing my screen. It's not me, honestly, it wasn't me. It's just, that's what Google decided to show me. Okay, so let me share my screen here just to show you, because this is pretty cool to see. Again, this isn't answering your question, Dawn. It's just more sort of fun stuff. There's my screen. So this is Monet's water lilies. He has, this isn't the exact image I wanted to show you. He's got blue water lilies here, I guess. And the thing is that the humans who looked at the scene he painted didn't see any blue water lilies at all. And what the issue was he had his lens, which is what gets cloudy and eliminates blue as we age, had been removed from his eye. He had had some problem with his eye. And so he didn't have a lens. Somehow there's a way that you still can see stuff. I don't understand the science or optics behind that. And so he was able to see blue colors that nobody else was able to see because he had no lens interfering with the light coming into his eyes. Anyway, I don't have many other examples. If you're in a classroom, on the other hand, there's all sorts of fun things that you can do. And one of which is, depending on the age of the kids, is you can get these spectrum glasses. Sounds like you're familiar, looks like you're familiar with them. You've seen them, Dawn?
Yes, I have several of them, including, I actually use the small, almost like the slide.
Right. My experience has been with the slide, there can be lots of challenges of them trying to find the thing. And that's where, again, just for completeness, that's not what we want to look at, but that is. There we go. In fact, that isn't what, this is another product. I give it away for free. If you're interested in measuring the sun's magnetism, talk to me later. It's not something I sell though. This is that little spectrometer that I sell to mostly high school, not elementary or middle school kids. You aim this at a gas tube. It's a lot to carry around. But I've gone to lots of education conferences. I mean, we've done dozens and dozens of booths at the AAS, at the NSTA, at the AAPT, if you're familiar with any of those organizations, and asked lots of teachers about using those slides. And I imagine your experience with the handheld slide isn't all that different than theirs, and that is it can be often quite challenging for the students to find the spectrum. So one thing you can do if you care to, and here I'm in selling mode, is you can look at using our spectrometer, if I can show it to you here again, our little spectrometer and gas tubes. You can go, the cool thing is, if you build spectroscopy into an outreach project that you're doing, if you go to a school, do the night thing, do the moon, do all the Saturn and Jupiter and all that. But if you also have a daytime activity, like with these solar telescopes that you've got, if you went into a classroom, it's not cheap. And again, I'm sorry that it happens to be something that I sell because my words should be considered a little tainted by that. But if you go into a classroom with one of these tripod mounted cameras and some sort of gas tube, and ask me, in private, and I'll tell you where you get them and so forth, you can actually now go to a chemistry or a physics teacher and say, I'm going to show your students spectra, or astronomy teacher. And spectra, it's interesting, physics teachers may cover it because, it's a topic, but physics teachers have so much to discuss that sometimes they don't have the time for it. Whereas chemistry teachers don't have any choice but to teach spectra, because the transitions are so intrinsic to the whole field of chemistry. So you could go in, honestly, if you had the time, and this may be the biggest draw of everything I've said tonight, if you're looking for something to do in outreach, look at our spectrometer, the little tripod thing and gas tubes. It's going to cost you about $500. And then go into classrooms, put together, and I love coaching people on this, and show students to start with the glasses. Those are cool. But the cool thing about being able to project it on an overhead, now you need an overhead projector too, and a laptop, is everybody sees the same thing at the same time. Everybody's going to see those lines that you can see there in that image. And they really get it. So anyway, that's the site for all that is this fieldtestedsystems.com. It's a little different. And again, my enthusiasm isn't because I want to fleece you or make money. It's because it can be, there's a gas tube, there's a spectrum, there's the peak. And check, if nothing else, check this video out to see how I teach spectra in a classroom. It can be real effective. Okay, I'll shut the flock up now. Other questions?
I think wearing the clown hair also helps.
What else? Anything? Whew, I'm off the hook. I can go up and get dinner. Listen, thank you all. I hope to hear from you. I'm always happy. I love the topic. I love answering questions. Thanks for your outreach. I hope actually some of you, I'll see you at the Star Party, Texas Star Party. Not this year, I think.
Possibly.
Yeah, I'd love to see you there. I'm also planning, I was going to be at Okie-Tex last fall. The thing is, the talks I give there will be pretty similar, very, very close to this talk. So the deal is, you know, like when there's a comedian, like Borscht Belt comedian or TV comedian, and you see them give their talk, and in the middle of their routine, they're going, oh yeah, you know, I mentioned, you don't want to go and hear them the next night because everything that looks so spontaneous, even that, oh, you know, I want to mention, is going to be mostly the same. So this is spontaneous. I like to dice it up a little bit, but all the same, it's the same talk. I hope to see you there. Or if any of you haven't been to NEAF in New Jersey, Dawn is looking like either she's been or she really wants to go. You too, Brian.
Only the virtual last year.
Virtual, yeah. What a I mean, it's better than nothing. Come to NEAF. Come to NEAF. It's the best thing. You'll see all of the vendors there. It will blow your mind. It really will. You do have to suffer for New Jersey and New York. I grew up there, so I can throw them under the bus. But it's a wonderful conference. I doubt this year's will happen even, but the following year should be huge. So come to my booth and say hello.
Nice.
And listen.
Before you go, I was just thinking about those handheld plastic spectroscopes. You know, the little, I have one, it's packed away from my move, but yeah, there you go. Yes.
These are sort of cool too. It's a private experience. You've got to get the angles right. And I'll tell you the biggest problem as a teacher for these is if you've got old eyes, you need bifocals to make this work. And now you're all doing all sorts of weird bifocal tricks. I can't read the scale on it. These are pretty inexpensive though. They're $3-4. I've asked, I think I've probably asked 1,000 teachers how they're teaching spectroscopy while standing at my booth. Literally 1,000, maybe 2 or 3 times that number. I was nervous at first, but now they say, oh yeah, we use the slides. And then I say to them, Dawn, this is where I was coming from. And then I'll say to them, now with as straight a face as I can, how's that working out for you? And that's where you get, like, it's really funny. All the nonverbal, you see teachers elbowing their colleagues next to them, and you see people laughing.
Well, I will play devil's advocate as someone who teaches astronomy to young kids, and especially to scouts, and especially to youth that are, no pun intended, totally intended, on the spectrum. Sometimes wearing things on their face is uncomfortable, so having the handheld small slide pieces does make it a bit more comfortable for them. So I tend to keep both as an option.
That makes total sense. I hadn't thought about that at all. There's certainly, I'm not as experienced in the classroom as you are, but I pretend I am.
You do tend to lose the glasses less because the slides can fall. However, the slides also seem a little bit more durable, whereas the glasses can bend and the actual, spectral, pieces can warp a bit. But, we were in outreach, so we're not expecting these objects and these equipment pieces to be pristine condition even after the first use.
Sure, that makes all the sense in the world. I wish I had other examples. When you're going into higher end classrooms, the poster which I showed earlier is teachers really love that poster, and for good reason.
I was going to show you, Tom, check it out. I have, oh, I don't know if you guys can see. I collect elements, periodic table elements.
Oh, very cool.
Yeah, and I'm like, I'm totally digging that poster. I'm absolutely got to get it as a companion for these guys. Magnesium, yep. Anyway.
I mean, I was actually introduced to spectra back in high school, and I don't think they would allow this much anymore in current school classrooms, but our science teacher actually, you know, had us taking individual elements and, you know, burning them in Bunsen burners and then looking at them through, you know, those sort of black plastic spectrometers.
Yeah.
Well, so if you can get away with that, that's a really great way, you know, to show it physically, you know, because they're not only seeing the light change in the fire without the spectral glass, but we can see how that spectrum breaks down. And of course, we can do that with the spectral tubes. Those are just a lot more fragile and they're a lot more pricey.
Yeah, since you're speaking of spectral tubes, I'll show you this product, which I don't sell either. This is a carousel. I don't know if you've ever seen it.
Not a carousel.
This is mind-blowing. I used to show it at my booth, but then people were ending up saving their money to buy one of these instead of my stuff. So truth be known, I don't demonstrate with this anymore. Really, I
shouldn't tell you I'm adding one to my Amazon cart right now.
So this is a cool device because gas tubes are cassettes. The reason gas tubes like the one I showed you earlier are a pain in the neck is, as you no doubt know, they have a duty cycle of about 30 seconds. They're really hot. They're a hassle to change, and they die. And the reason they die is because air infiltrates through the wire that goes through the glass, through that hole.
Oh, wow.
This device, these are completely sealed. They inductively couple internally here. And so I've left them on overnight. And the cool thing is you can rotate it to different elements. So the switch, and this is durable. You can just carry this thing around. If you want to buy one, again, we're losing a lot of people who aren't educators. Contact me at Arbor Scientific is where I'd recommend you buy everything. Good vendor, but they're all the same. They're made by the same company.
What is it called again?
This is called a
Spectrum Tube Carousel.
Spectrum Carousel.
I'm on their website right now, and it's like, ooh, your RSpec classroom spectrometer is actually less expensive. So there's a bonus for you there.
Yeah, exactly. Now I wanted to brag about this poster and maybe just to entertain everybody. This story here. He's now got the poster hanging in his office. So this is on the street outside a talk he gave. This is the second time I met him, and he came out at like midnight. He was doing a meet and greet. We calculate, not that it matters. He's a great guy. We calculate he probably makes 100,000 a week when he's traveling. I mean, because he fills these halls with, a couple thousand people. But he came out, and there are like 6 or 8 of us behind a Jersey barrier. They wouldn't let us get close to him this year. And, he looks over and, well, Dr. Tyson, we're yelling. He's tired. He wants to go to his limo. And I've got the poster hanging out over the Jersey barrier. And so he's people call him over. So he's sort of coming over and he looks up at the poster and he goes, wow, that's brilliant. Brilliant. Why hasn't anybody thought of that before? And I'm going, ding. And then his next line is, can I have one? It's like, yeah, I bought 2 in a poster tube. Here it is. And it's got my business card inside of it with special non-mar tape that my wife, business partner, had carefully gotten. We're ready. I never heard back from him. Bupkis. I'm thinking, come on, Dr. Tyson, at least, and so now I'm thinking, suppose, some people think about winning the lottery. So I'm thinking, suppose I get a phone call, Tom, this is Dr. Tyson, Neil Tyson, I love the work you're doing. Because the year before I'd shown him samples of the sort I showed you in my talk, and he got all excited. I mean, really, he's from down there in Texas. He went to school down there, as some of you may know. And he said to me, ask me a question, a typical Texas question I'd never heard asked before, certainly not in this context. I've been telling him quasars and stuff. And he said, meanwhile, there's all these people queued up who are having him sign the programs. And as soon as I start talking science, he just drops them. I mean, he's like signing stuff while he's talking to me. So he says to me, what are you packing? I go, what? What are you packing? I said, pardon me?
he said, what kind of aperture are you using? So I told him 8 inches and stuff. But so he went with the poster. I did say to him, and it turns out he was visiting for 2 nights. But coincidentally, I was going to be out at a high school with one of these solar telescopes the next day. And so I said to him, just on a lark, I said, hey, Dr. Tyson, I'm going out to an underprivileged school tomorrow, which it was, with a solar hydrogen alpha telescope. Do you want to join me? So, he actually didn't say no. He stopped. He was thinking. And either he's really polite or he was telling the truth. He said, I'm all booked up tomorrow. My dance plate is full. He was going to be in town. And as it turns out, the following day after that, I heard he spent the whole day with the Seattle Seahawks talking physics. So I think he probably was booked. Can you imagine if he'd said yes, the next question would have been, do you want to pick me up in your limo or should I pick you up in my 2000 Legacy station wagon? Either way, it's fine with me. So, and also there's the poster up in the Sophia Boeing, which is sort of fun to see. Anyway, listen, thank you all so much. I appreciate it. Thanks for doing the outreach that you're doing, Dawn, and the rest of you. Thanks for hopefully enjoying yourself tonight. And I'm just looking for a way to stop everything. Have a